All right, so let's talk about shell sort in this video, just a quick video over that. Shell sort is a sorting algorithm that's based off of insertion sort. So before we talk about shell sort, let's actually look at insertion sort real quick and see how that works. So let's pull up insertion sort here. Let's say I have a list here. Let's go with, I'm just gonna come up with some random values to put in here. 2, 5, 1. Should go with 7, 6. Okay, let's say this is what we have right now. Oops, I'm missing one more number. Let's put 3. I want to get 8 numbers in here. That's all 8 numbers. All right. So let's look at insertion sort. The idea behind insertion sort is that you sort everything into the left. Right. So you assume that the left has your sorted list, and then you sort things into the left. Because if you have a sorted list, it's easy to know where to sort things, right? So for example, if I have 0, 1, 2, 6, 8, and I want to sort in a 4, because this is sorted, I just know, okay, well, I'll check to see if I can put it before the 8, and I can, so it goes there. So I have 4 here now. And then I say, okay, well, can I put it before the 6? I can put it before the 6, so it goes here. And then I check, can I put it before the 2? I can't because 2 is less than 4. And I don't have to check 1 or 0 because since this is sorted, remember, this is important. Because this list is sorted, then I know that if I can't put it before 2, all the numbers to the left of 2 have to be smaller than 2. So if it can't go before 2, it can't go before any of the other numbers, right? So that's kind of an invariant of insertion sort, which means that the list you're kind of inserting into, that's where you get the name, has to be sorted. All right. So in this case here, well, where do we start? Well, we know that the first item has to be sorted because any list of one item is automatically sorted. So we take the first item, which is 0, and we say, okay, well, can we put 0 anywhere? Well, first we check with the element to the left. 0 is less than 4, so we swap it. So we get 0, 4. Actually, let me just start crossing things out. So 4 goes here, 0 goes here, and then because we've reached the beginning of the list, we don't need to go any further than that, so we stop there. And then when we want to do 2, well, we compare 2 to 4. 2 can be swapped to 4 because 2 is less than 4, so we swap it. And because we just swapped, maybe it's also less than the numbers before it. We don't know, so we check. 2 is not less than 0, so we don't do any swaps, and we're done. Compare 5 to 4. 5 is not less than 4, so it just stops. And because it's not less than 4, it can't be less than anything else before it, because everything before 4 has to be smaller than 4. So we stop there. Now we do 1. So we compare 1 to 5. 1 is less than 5, so we swap. And because 1 is less than 5, it might also be less than the numbers before it. So we check again. 1 is less than 4, so we swap. And 1 compared to 2, 1 is less than 2, so we swap. And we compare 1 to 0. 1 is not less than 0, so we stop there. Then we continue on with the rest. So 7 compares to 5. It's not less than 5, so we know it's not less than anything else. So we stop there. 6 compared to 7. Put 7 here, 6 here. There we go. And since 6 just swapped to 7, maybe it's smaller than everything to the left. So we check. 6 is not less than 5, so we don't swap. There we go. And then with 3, well, 3 is less than 7, so we swap. And since 3 is less than 7, maybe less than things before it, it is less than 6, so we swap that. And we check again. Less than 5, so we swap that. Then we check again. 3 is less than 4, so we swap that. And 3 is not less than 2, so we stop. And now our list is sorted. Right now, if you notice, we had to sort toward the left. Why do we have to sort toward the left? Because we're doing insertion sort, we have to make sure that the list is growing. Like when we're inserting into a list, the list that we're inserting into, we have to make sure it's sorted. So if we're starting from the left and we're assuming that the left is sorted, we have to check in that direction. If we check in this direction, that's wrong because if we start off with this side of the array and we try checking in that direction, that would imply that this direction has a sorted list, but it doesn't. If we're starting from the beginning of the array, the part that has a sorted list is on this side, right? If you look at bubble sort, which is the opposite of insertion sort, where instead of checking if the number is less than, you check if the number is greater than, well, you actually have to start here, because if you're assuming all the numbers are sorted, then you have to assume that in that direction it's sorted. And you're putting, because you're going greater than, so everything has to go in this direction, which means everything here has to be sorted. So you start on the end. But that's insertion sort. So let's talk about shell sort real quick. One thing about insertion sort is that you have to do a lot of comparisons, a bunch of checks, right? And in the worst case, if your list is completely reversed, you have to do n squared checks, or technically n times n minus 1 over 2. But you have to do a bunch of checks, and it just takes a long time. The idea behind shell sort is, well, if you have a randomly organized array, it's likely that elements are far away from their actual position, like their sorted position. So instead of doing one check at a time, instead of only checking one slot at a time, why don't we do big checks first, get things roughly sorted, and then we can do the smaller checks. That way we don't have to do a bunch of checks, right? So for example, if 0 was here, or let's say -1, right? If -1 was here, let's put it here, right? Because we know -1 is smaller than everything here, we're going to have to check with 7, then 6, then 5, then 4, then 3, then 2, then 1, then 0. And then we finally get it put it in its correct spot. If we had maybe moved -1 in this direction earlier ahead of time, then we wouldn't have to do as many checks. So that's what shell sort's all about. It's saying, well, first check elements like that are a good distance away from each other, and then we can start sorting by smaller amounts. And so we have this idea of like gaps or increments. So let's talk about that real quick. Let me take the exact same array. And there's a lot of research that goes into what series or sequence of gaps is best for shell sort and what makes it fastest. I don't know any of that stuff. So we're just going to go with a very simple sequence of gaps where you take half the array size and just keep dividing in half until you're sorting by 1, right? Because at the end of the day, with insertion sort, you have to sort every element by looking at the element next to it, because that's the only way you can be sure that it's sorted, right? So eventually we have to end in 1. That's important. End here. Where do we start? Well, this array has a size of 8, so I'm going to start at 4. And then I'm going to go to 2, and I'm going to go to 1. Right, start here. So we start with larger gaps. If we start with larger gaps, then it's likely that we can move elements closer to where they're supposed to be before we start doing this one-by-one checking. All right, so what does it mean to sort by gaps of 4? Well, that means that if I were to look at every 4th item, it would look sorted, right? So right now, if I were to look at every 4th item, I'd be looking at 4 and 1, and then 1 and 3. So this list would be 4, 1, 3. And now I'd be looking at 0, 7, and well, that's it. There's no more, so we stop there. Actually, did I do this? Oh, it's actually not 4, 1, 3. Because 3 is not, we say every 4th item. So it'd be 4 and 1, and then there's actually not a 4th item, my bad, so we don't do that. We do 0 and 7, and we do 2 and 6, and then we do 5 and 3, right? So our sublists, these sublists here that we have a list with 4 and 1, 0, 7, 5 and 6, and what is the last one? Not 5 and 6. It is 2 and 6. My bad. So 0, 7, 2, 6, 5, and 3. These are our lists right now. If I were to look at this, well, actually most of these are sorted. Zeros, or half of these are 0, 7, 2, 6. These lists are sorted. 4, 1 isn't. 5, 3 isn't. But how do we actually sort these? Well, we just do normal insertion sort. It's like here, where instead of checking the item right next to you, you check the item further away from you. That's all it is. So when I start, well, remember we have to compare in this direction, right? So I can't start at 4 because 4 actually would have to compare with an item 4 to the left of it because we're always inserting into the left. So I actually can't start at 4 or 0 or 2 or 5 for that matter because none of these have an element that's 4 to the left. So I actually have to start at whatever gap I'm starting with. If I have a gap of 4, I have to start at the 4th, or I have to start at index 4 so I can compare it with something to the left. If I'm starting at gap, say 2, I have to start at index 2. So that way I can compare to the item 2 to the left, right? In this case here, we're starting with gap 4, so that's index 1, or value 1, index 4. And we say, okay, well, is 1 less than 4? It is, so we swap it. And it's just like insertion sort, right? Except here, instead of subtracting 1, you subtract 4. That's it. And then we check the next series of gaps, right? So that's one of the sublists we sorted. Now let's sort the next sublist. So 7 compared to 0, it's already sorted, don't need to do anything. 6 compared to 2, already sorted, don't need to do anything, right? And when I say already sorted, I mean like we check to see if we need a swap, and if we don't need a swap, we stop there. Just like how above here, once we found out we didn't need a swap, we could just stop there. Same thing here. Compare 3 and 5, well 3 is less than 5, so we swap them. And then we try to check, like if I want to be specific here, I was like, okay, well I just did a swap, so maybe it's less than the item before it. But it turns out this is at the end of the loop, or at the end of the array, so I can't go any further back. So we just stop there. So now my list looks like this. It's 1, 0, 2, 3, 4, 7, 6, 5. And if I were to look at every 4th item, if I had my perspective was very narrow and I can only look at 4th items, I would think that this array is sorted is already sorted because we have 1 and 4, 0, 7, 2 and 6, 3 and 5. The array looks sorted to me. Now clearly it's not, but that's because we haven't sorted by smaller gaps yet. Now let's move on to the next set of gaps. Gap of 2. So in order to be able to check with something to the left, we have to start at index 2. It's the smallest thing we can start at. So we start at 2. But let's actually look at the sublist real quick. We're doing with 1, 2, 4, 6. So our actually looks like this. It's 1, 2, 4, 6. All right. Well, that's actually pretty good then, right? So we have that done. And then 0, 3, 7, and 5. So this second sublist we have is 0, 3, 7, 5. So the question is, once I'm done sorting by 2s, both of these lists should look sorted to me. And right now, this one isn't. But well, let's continue on and see what happens. So we start with 2. Compare 2 with 1. It's not 2 is not less than 1, so we stop there. Then we move on to the next one. 4 and 2. 4 is not less than 2, so we stop there. 6 and 4. 6 is not less than 4, so we stop there. Then we move on to the next set, which is 0, 3, 0, 3, 7, and 5. So compare 3 and 0, 3 is not less than 0, so we don't swap. 7 and 3, 7 is not less than 3, so we don't swap. 5 and 7, 5 is less than 7, so we swap them. And this is important. We continue checking, just like how over here when we swap something, we keep checking. So we do 5 and 3. Well, 5 is not less than 3, so we don't swap it. So we just leave it as is. Now we're done. Well, we move on to 7, actually, technically. We move on here, compare 7 and 5. 7 is not less than 5, so now we can stop. And so now we have this list, right? So if I were to look at every second item, we have 1, 2, 4, 6, and also 0, 3, 5, 7, both of which are sorted. So once again, if I were to only look at every other item, this would look completely sorted to me. Now we sort by 1s. So let's do that real quick. 1, 0, 2, 3, 4, 5, 6, 7. So this is, if you're sorting by gaps of 1, that's basically insertion sort. So we start with the first index that we can actually sort by, which is 1. We check to the element right next to it, because that's what an increment of 1 is. 0 is less than 1, so we swap. And then we check again, but 0 is at the beginning of the list, so we can stop there. 2 is greater than 1, so we don't swap, so we stop there. 3 is greater than 2, so we don't swap. 4 is greater than 3, don't swap. 5 is greater than 4, don't swap. 6 is greater than 5, don't swap. And 7 greater than 6, don't swap. Right. And if you notice here, we actually did far less checks than we did up here, right? So how many swaps did we do? Well, let's just count the number of times I crossed the number out, because that indicated a swap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we're at 19 x's here. Right here, I only have 1, 2, 3, 4, 5, 6, 7, 8. That's it. Right. So this had like 19 crosses, and this one had 8 crosses. So we can see that because of shell sort, because we started moving things further back much earlier, then we didn't have to do as many checks later on when we're only doing increments of 1. All right, so that is shell sort. Hopefully that helps you guys understand. Just remember, this is essentially the same as this. We're just changing the gap size. Size differs. So with shell sort, you're basically running insertion sort over and over again, but with different gap sizes, until you eventually reach 1, which then you're just running insertion sort. But by the time you're running insertion sort, hopefully your list is more sorted, so you don't have to do as many checks. And that is the idea. All right, so that is it for shell sort.